My, to, my today's session is based on a topic which is called T distribution. It is also a kind of sampling test. First of all, before I share any screen, I'm going to say a few words about this T distribution thing. The entire large sample theory was actually based on the application of normal test. However, when the sample size is small, the distribution of the various statistics, by statistics here we actually mean the sample measurements, are actually very far from normality, and as such normal test cannot be applied if sample size is small. You know that the sample size is small when the size is less than 30. In such cases, a special type of sample tests are actually applied, which are called exact sample tests in general. This exact sample test was actually pioneered by the statistician whose name was W.S. Gossett. Now, there is a very funny story about this statistician. Gossett was actually doing his PhD works in some other subjects. I cannot recall right now what subject it was, but that was indeed not statistics. But he was deeply fond of this particular subject, statistics. Okay, and in his topic that on which he was actually researching, statistics was actually, I mean, there was a tremendous kind application of statistics in his field. I cannot recall whether the field was chemistry or biology, but Gossett found some sort of interest in this particular field of statistics, and he decided to pursue some research work on that. In his days, and now also, the research guides, they do not want their students to go astray here and there. And if you do research in your later career, you will find that you are always being supervised and CCTV'd by your guide. And whenever you will do the research and you will write the paper, and you will happily go to show that particular paper to your guide, then the guide will not say anything about uh, um, the research work, but he will be, or maybe he is going to say, but first of all, he will be deeply interested in something else that I'm not going to mention. he will try to find it out by yourself. Okay, try to get this experience by yourself. Okay. Not everybody is going to do research work, so the discussion of this matter is irrelevant. Anyways, so Gossett was very much afraid of his guide, and he didn't want his guide to know that he was pursuing some sort of research work in statistics. So he wrote some paper. So he wrote some research paper on statistics. Very famous papers were they. But he didn't use his name over there. He didn't write that this such and such paper was by W.H. Gossett. Rather, he used a pen name. You know, authors often use pen name, okay, to write their stories and poems, etc., novels. So he also used a pen name to write his research work. And it's very funny, and you will be amazed to know that W.H. Gossett's pen name was Student. Okay. And in one of his papers, he found a statistical distribution that a particular population is going to follow. And he named this distribution. He didn't name this distribution. He found its form, its probability density, its cumulants, its moment generating function, everything he studied. But in later course, people, or rather statisticians, used to refer this particular distribution as students T distribution. They used the letter T from the word student itself, and often it is called students T distribution. So this is a very funny story, and students T distribution is actually is a kind of exact sample test which is applied when your population from which the sample is being selected is far from normality, and the sample size is also very small. Now, you have to keep in mind also in the fact that this exact sample tests can, however, be applied to large sample also, though the converse is not true. That means under some conditions, if you have large samples, you are I mean eligible to apply the exact sample tests, because these tests are designed in such a manner. But in small samples, you cannot apply the large sample theory. Okay, so that's why that's why I have I have said that the converse is not true. Although the exact sample tests can be applied to large sample, reverse is not correct. And in all exact sample tests, student T distribution is not the only exact sample test. Other exact sample tests are also there. But in all the exact sample tests, two basic assumptions are actually considered. Not two assumptions, one assumption, fundamental assumption is considered. The assumption is the population from which the sample will be drawn will be considered as normal, or the population is normally distributed. Okay, that particular assumption has to play before you go to apply the exact sample test. That means, see, you are going to choose the sample with a small size, not intentionally, because of some reason, because you are not able to get a large sample. There may be various constraints for which you are actually subjected to small sample, but this small sample is a part of the population which is very large. Whenever we say that the parent population must be normally distributed, by that we mean that from which the population from which either the large sample or the small sample has been selected, that population, that large population, that has to behave with respect to the normal distribution. Population parameter mean has to be known, population parameter variance has to be known, and so and so. Okay, so students T distribution is a kind of probability distribution which has a specific probability density function. I am not going to discuss about the detailed mathematics of students T distribution here. I am going to apply students T test in hypothesis testing, for which I actually shared this particular statistical chart with you in the Google Classroom last night. I hope you can see my screen. This statistical chart, actually, you can see that it consists of several pages, from 16 pages altogether. And in today's class, we will be concerned about this particular page, which, as you can see, gives you the percentiles of the student T distribution. And this figure that you have to consider, this figure is actually telling you that the population is normal. Because how can I say that? Because the point zero is written over here. That means the variable is standardized, whose mean is 0, and student's T value at some level of significance is shown to be like this shaded portion which we are interested about, and it is denoted by the alpha. Okay, and different percentiles for different level of significance, like 0.40, 0.25, 0.10, 0.05. 0.05 means 5% level of significance. 0.10 means 10% level of significance, 0.01 means 1% level of significance. All these things have been considered over here. And here you can find the sample sizes. For different sample sizes, these probabilities have been calculated. How did they calculate the probability? Okay. That I can, at least I'm going to, because since you are learning it, so at least I'm going to write the probability density function of this T distribution. Let me show you the shape of the density function. Okay. And whether you are scared to see its shape or not. Anyways, right now I'm very much scared about its shape. So that's why I'm not going to discuss in details. Something like this is the shape of the probability density function of the student's T distribution. This is the beta function. You studied beta function in the first semester course, beta mn. So this is the beta function, and T is a variable fluctuating in this real line. And nu is kind of another kind of parameter, okay, which is to be known to know about the distribution. And this particular probabilities that you can see on your screen is actually obtained by integrating it from some ranges for some specified ranges. So we have this particular chart with us. We are going to apply this statistical chart in exact sample tests. And now we are going to see that what are the cases where exact sample tests will be required. Okay, for which I'm going to share some pages from the book by Montgomery, book by Douglas Montgomery. Okay, it's applied statistics book written for engineers. It's also a very good book because here the detailing of this exact sample test is actually very, it's written in a very wonderful way. Not the section which I'm actually showing you right now, but the story actually started from some other previous pages. Here this particular this particular article that you are seeing right now, it's the continuation of our hypothesis testing chapter, where we will be interested in finding out the validity of the hypothesis about the population parameter, which is population mean. Okay, but the only difference is that when we studied the significance test of single mean of the population, we use the formula x bar minus mu by sigma by root over n, and we use the large sample test. This mu was having some value mu naught, and under the assumption of this null hypothesis, we calculated this particular test statistic. But condition was that one extra condition was also mentioned, that this population standard deviation was known to us. So that's why we could use this particular large sample test over here. Student T distribution or student T statistic becomes very much helpful to us when this population variance is not known to us. We do not have any idea about the population variance. Actually, then we apply the student's T distribution, the exact sample test. Okay. The formula which is written in front of you is actually very similar to the formula which you studied earlier. Let me write the formula of the Z statistic for this test of significance of single mean. So actually we use the small letter, so that's why I'm writing in small caps. We can use capital letter also. So the formula was this, isn't it? See the structure of the formula. They are very similar to one another. X bar, the mean of the samples, is their population mean with some value is present. Small sample size small n is present, but what is not present is sigma. In place of sigma, we have capital S. And it is also mentioned that this statistic, capital T, follows student's T distribution. That means probability density function of this statistic is having the form which I wrote a few minutes ago. And another important statement is mentioned over here, which is called degrees of freedom. That this particular student statistic is actually following T distribution with n-1 degrees of freedom. Now, this term degrees of freedom is actually new to you. What is degrees of freedom? Let me explain. Since sigma is not known to us, sigma is not known, so we want to estimate sigma by some other statistical tool. Sigma hat, this notation is actually stands for estimator of sigma. What sort of estimator can we use to estimate sigma? There are two options. One option is we can calculate this standard deviation by our usual formula, which goes like this. Or we can also calculate the standard deviation by our formula with some little modification where we are going to divide by n-1 and not by n. In any statistical book, I can refer one such book to you. This is easily accessible. Most of the students have this book with them, I have come to know. The book is not very good, but it was used. It has been in market since 60s. It's by one of the professors from Calcutta University, N.G. Das. He wrote statistical methods. In this book, you can find this proof also, that he has shown that he has proved in his book that expectation of S is actually equal to sigma, but expectation of small s is not equal to sigma. So capital S is actually not a small s is not actually a good parameter of sigma, a good estimator of sigma, but capital S is a good estimator of sigma. And various other books are there where you can find this particular proof. Okay, not in N.G. Das, other books are also there. If you do not find it in any book, then you can find it in the internet also. The proof is available. The important point is that we have to erase this particular estimator from picture. That will not estimate our unknown parameter sigma. So only possibility remaining is to calculate this quantity, capital S. But to calculate capital S, what we need to do, we have to divide this particular term by n-1, sample size minus 1. And therefore, this quantity, because you are reducing your sample size to get a good estimator, that is actually called degrees of freedom. Degrees of freedom in general is called the number of independent variables which is required to study the system. Number of independent variables, you already know what do you mean by independent variables and dependent variables. So if the sample size is n, there are n variables, because n different sizes, if you consider each of these sizes variables, then one particular variable is becoming redundant. Whether you use it or not, that doesn't matter actually. So we actually reduce the size by 1, reduce the size of the sample by 1, and that accurately estimates the population standard deviation. And therefore it is mentioned over here that the student's t statistic follows t distribution with n minus 1 degrees of freedom. Okay, now why am I putting some more time on this? Because you have to keep in mind that whenever we are going to calculate something regarding students' t statistic, some sample size will be there. Suppose the sample size is 10 with which you are calculating. Now, after the calculation, you are going to get your t value. That t value will be tested with, will be compared with the tabulated t values, not for 10 degrees of freedom, but for 9 degrees of freedom. Okay, so for sample size 10, we are going to select this row corresponding to 9. If the sample size is 9, we are going to select this row with sample size 8. So one sample size minus 1, that is going to be selected for drawing your conclusion. So we have this formula, but you see that there are no changes in designing the null hypothesis and alternative hypothesis. Just the way by which we define null hypothesis and alternative hypothesis for testing the single mean, that has been maintained over here. And obviously you see that this is a two-tailed test. Okay. Now, let us read this particular paragraph that is written over here. If the null hypothesis is true, T naught is the specific value of this quantity when we put the respective values of different items that are present in the formula. So T naught is the value of capital T if it has a T distribution with n minus 1 degrees of freedom. Then we call this null hypothesis is true. When we know the distribution of the test statistic when H naught is true, this is often called the reference distribution or the null distribution. We can locate the critical region to control the type 1 error probability at the desired level. In this case, we would use the T percentage points minus T level of significance at alpha by 2 with degrees of freedom n minus 1 on the negative side, and T alpha by 2 n minus 1 on the positive side. And critical region as before will fall when T naught exceeds this value on the positive side, or it is less than the value on the negative side. The analysis will be similar to the way by which we actually did it in case of large sample theory. Okay, just a minute. Now, so this is the way. I'll share the note with you later on, but right now, if you want, you can take a screenshot of that. So in one sample t-test means a single population. One sample means one particular sample has been chosen, and population is only one population is present. When we actually draw two samples, it is wise to assume that two populations are actually playing behind the screen. Suppose I'm asking two particular students to draw sample, then I'll expect that these students, and I'm actually interested in actually two different populations, but here I can be misguided by my experimenters. They can select the sample from a single population, but they can pretend that they have done it, they have drawn it from two different populations. That I want to test in two sample test. But if I'm sure enough that the thing has been drawn from, if there is only one sample, there is no question of having two different populations playing behind the screen. So therefore, such type of testing is called one sample test. Basic rule is that you have to set your null hypothesis. Nothing has been mentioned about alternative hypothesis here. because whenever you are assuming null hypothesis it is always associated with alternative hypothesis. The test statistic is already known to you, and these are the criteria by which you are going to reject your null hypothesis and accept your alternative hypothesis, and so and so. Okay, when I'm writing that H1 is equal to mu not equals to mu naught, that means you are actually accepting the alternative hypothesis. Rejection criteria is this. Rejection criteria of what? Rejection criteria of not the alternative hypothesis. Alternative hypothesis is accepted on the basis of the rejection criteria played on the null hypothesis. You already know this rule. And the chart which is written over here in this block, this chart has been shown with respect to this diagram. 3 diagrams have been drawn over here. Each of these diagrams corresponds to each of these cases. First diagram corresponds to two-sided sample. Two-sided test. Second diagram corresponds to the upper tail test. Third diagram corresponds to the lower tail test. And you have to keep in mind what level of significance you are playing with and what sort of test you are actually doing when you deal with this T statistic. And when we talk about one-sided test and two-sided test, that will be decided by just the way by which we decided in the case of large sample theory, that in null hypothesis, mu naught is the equality symbol must be present. The one-sidedness or two-sidedness will be decided by the structure of the alternative hypothesis. In this respect, I must declare one thing, that sometimes in some book you may find that the null hypothesis is written in the following manner. Suppose they have written the null hypothesis in this manner and alternative hypothesis in this manner. This is also true. Remember, I forgot to mention this earlier, but this is also true, because you have to just make sure that equality symbol is present, because everything which is being tested is based upon the basic hypothesis, this null hypothesis. The hypothesis is hypothesis of no difference. But if someone writes like this, say for example, he is writing mu greater than mu naught, and in alternative hypothesis he is writing mu less than or equal to mu naught, then this is wrong. Alternative hypothesis cannot include equality symbol. So just keep this in mind. Okay. Okay, so now let's get back to a particular problem which is shown over here. I'll quickly read the question because the question is very long. I'm just interested in finding the solution. I'm interested in discussing the solution of the problem, because the p-value part of this particular problem is actually very important, and you have to put your attention to that part, because my today's discussion is actually I'm doing this discussion to let you know about the p-value part of this kind of exact sample test. So I'm going quickly reading this particular problem. The increased availability of light materials with high strength has revolutionized the design and manufacture of golf clubs, particularly drivers. Clubs with hollow heads and very thin faces can result in much longer tee shots. Especially tee shots is kind of term which is associated with the golf, especially for players of modest skills. This is due partly to the spring-like effect that the thin face imparts to the ball. Firing a golf ball at the head of the club and measuring the ratio of the outgoing velocity of the ball to the incoming velocity can quantify the spring-like effect. The ratio of velocities is called the coefficient of restitution of the club. An experiment was performed in which 15 drivers produced by a particular club maker were selected at random and their coefficients of restitution measured. In the experiment, the golf balls were fired from an air cannon so that the incoming velocity and spin rate of the ball could be precisely controlled. It is of interest to determine if there is evidence, alpha is 0.05, to support a claim that the mean coefficient of restitution exceeds 0.82. the observation follow, and it is given over here. Now see, it's a very long question. Various technical terms are there. Most of the terms are not known to me. Some terms are, you know many more terms better than me. I am a statistician. I have just read the question, and I am just trying to find out the things which I am actually interested in. Okay, I don't want to know what is t-shorts. I don't want to know what is spring like effect. Okay, here in this entire paragraph, the technicalities of the situation, the situation has been properly mentioned. But since I'm a statistician, I want to give conclusion on the system. I have got kind of overview of the system, maybe not in details, but okay, I can understand something is what is being said over here. But what are the important terms for me as a statistician in this particular problem? In this particular problem, the important terms for me are 15, because this is my sample size, and I shall count that whether 15 items are present over there and try to identify that this sample size is pretty small. It is less than 30. But what is this sample? This is sample of drivers. Okay, and now this drivers, the population of these drivers is not a small. It's not of small size. This population is large. I shall assume that this population of drivers actually behaving normally. That is my assumption. On the basis of this assumption, I am going to apply this t-test. Now, in this particular case, large sample test will not be applicable. Z I cannot apply for another reason. In this case, standard deviation is actually not known to me. We do not know the standard deviation. It's not given. So therefore, large sample test cannot be applied. But in large samples, exact sample tests can be applied, as I mentioned a few minutes ago. Now, what is written over here? They has predefined the level of significance at the point alpha equal to 0.05. They are asking us to test the hypothesis as 5% level of significance. And why should I test it? To support a claim that the mean coefficient of restitution exceeds 0.8. Okay, so they specifically tell me that they want something greater than 0.82, but I cannot use the this greater than symbol in the null hypothesis. So generally, naturally, I'm going to write mu naught equals to 0.82 in the null hypothesis and mu naught equals to greater than 0.82 in the alternative hypothesis. So it is a one-sided test, which is clear from this line. They have already calculated the mean of these items, which is sample mean. You can use capital X bar, you can use small x bar, doesn't matter, but you have to make sure that whatever symbol you are using, the meaning of that is clear to you. Okay, if you want to verify this, this particular calculation, you can do it by yourself with Excel or with calculator, whatever. Small s, this deviation has been calculated, but I'll ask you, all of you, to calculate this deviation and to check it, the calculation, because here although they used the symbol, I don't know why. Sometimes they are using capital S and sometimes small s. Parity is not being maintained. Or maybe it is a printing mistake. To calculate this standard deviation, they divided this summation, the xi minus x bar whole square, by not by 15 but by 14, and therefore degrees of freedom reduced to 14 degrees of freedom. It will be tested. How did they calculate this particular standard deviation? They calculated this standard deviation. First of all, if I consider this as xi, x1, x2, x3, x4, x5 in this manner, so they have taken the difference of this first value and the mean, they squared it, second value and the mean, squared it, and so on. 15 items square of the difference of the values from mean of these 15 items have been considered. Their summation has been taken and divided. They divide this summation by 15 minus 1, 14. Okay, and that's how they got small s. Now you see, whatever I have told you, the way it has been written over here, and they substituted this T naught, and x bar is minus T naught is x bar minus mu naught by s by root over n. Here in n, you are going to put not 14, but 15. Remember, just to calculate small s, you are going to divide by n minus 1. But whenever you are going to substitute this sample size over here, that should be the actual sample size. So here you are going to divide by 14, and here you are going to divide by 15. Keep this in mind. Okay, don't be confused. Degrees of freedom is associated with the calculation of the deviation only. Ultimately, what are they writing? They are writing that they have calculated the value T naught. They will reject the T naught. Okay, they will reject the T naught if at 5% level of significance and 14 degrees of freedom, the tabulated value that we have, if the calculated value is greater than that tabulated value, they are going to reject the null hypothesis. Now let us try to check whether this value is correct or not. The statistical chart which I'm actually presenting to you, this chart has not been taken from this Montgomery book. That chart, the statistical chart, I have splitted the PDF file from the book by Sheldon Ross. But I wanted to show you that any book you use, you are going to get the similar result. Now I'm going to present the statistical chart taken from Sheldon Ross, and you see at 14 degrees of freedom, at 5% level of significance, 5% level of significance, the tabulated value is 1.761. So these are matching. Okay, and if I can find my tabulated value to be exceeding this value, I am going to reject my null hypothesis. So that is the rule. So they substituted everything. See, the sample size 15 has been taken, and after calculating this, they obtained 2.72, which is exceeding the tabulated value of the T statistic, and they are going to reject the null hypothesis at 5% level of significance. It is called the direct testing. P-value has not yet been discussed. In the block, several other values they have mentioned. Somehow they calculated p-value also. I'm going to explain later on. But anyways, here the block has been calculated by some sort of statistical software. So the null hypothesis is getting rejected over here. In the next section, I'm going to calculate, I'm going to tell you about how to calculate this p-value in the case of exact sample test. Okay, so I'm stopping right now over here. In the next session, you are going to put your attendance.